Yeah. Okay. Let's go into it. So I guess like the title has already been said. So let's just take a step back and just to like just to remind you about like what in general zkEVMs are solving. Okay. So in general, well, theorists have to just go. So everybody is about okay, we will just typically state conditions of both for the that different applications specifically designed to assist credit class choose. So did it pop up like a lot just with dot was cheaper some made with CDF setting scale very factor. Okay. The thing is they still keep whole SDA paragraph under that isolated. I think more material recommend shorter. But like at least they buy the most very limited use. Pretty much same numbers. So there are still trade-off. Basically like whether stealing fish are still there. Damn. But let's say this way, there was still less so more like practice. So to say an active unfortunately. So like it will be Saturday. It's like some of security concerns of the EVMs started already recently. It's like that I just talked about them critical like a year or something. But they thought it right. We did that at the right, like recently, literally like 2 3 well something. We'll look at that. We'll get to that. Just among other trade-offs that are not released and apply this about the because just and validate their issues, which are mainly not good, but anyway, and yeah, so the wall, the bit yes, hardware, the wall, security, same with it. So we should do that, and how that should be solved is like a little bit of being this should be is that you gotta be able to all be composable, kind of keep the whole thing and out for awareness. You got deep liquidity. It is possible. The universities on here. At the same time, you have still be secure enough. So secure enough. Whereas the yes, like before Windows, like is that secure enough? I mean, yeah, adults. That's like security a little bit of concern, which kind of was a year ago. And most of them, most of those current apps are defined via, just managed circuit efficient, like in the students, ETSLs, and like, I don't know, just from HTTP or whatever it is. So all of these kind of rusty DSLs, CDP DSLs. So the question is it winnable? Does it work? No. Here we go. So that's like, I know that this issue is not only about a circuit. Okay, let's be honest. There was like different reason for that as well. But in general, there is also like an issue. And that's, the first one. And I bet it's not the last one. And, just in case, auditability. Was it audited? Yes. Same circuits, different company did the audit. Did it help? No. So that's the nuance. So we gotta somehow improve the auditability of, the way we define circuits, because otherwise it's just, something not good. Then next thing which we're facing is upgradability. I mean, let's be honest. Every significant EAP gets like, EVM behavior changed, right? So somehow, like sometimes it's a minor change, sometimes it's a major change, like adding a new opcode. Like again, these things like, long-awaited EEP will add a new opcode, and what we required to do, you will be like required to redo the circuit, not like maybe not all of it, but like to add something in there. Definitely re-audit that, definitely redeploy that, definitely, do the whole thing again and do the whole thing again. So several iterations, and this concern will stay valid. So that's the thing. The next thing is keeping up with all the changes. In fact, within the circuit, manually defined circuit. I mean, like, come on, this is like a screenshot from eepz.org, which shows like the basically core proposals, and about half of them actually affects EVM behavior in some way. about half of them, maybe more. Okay, so that's like, and just imagine the resources you need to keep up with all these updates while manually doing the circuits. I mean, that's a big team. You need to, I mean, we know that. We know that, like most of these, fellows who are present in India also know that. So, I mean, can we do better? What should we do better? I mean, we can do that. If we compile the circuits, if we generate them from something human readable, from something average developer readable, from something high level. So that's basically what we did. Right? We did the compilation of zkEVM via basically circuit-based zkLLVM target. So we got some like pinpoints okay in here. We'll walk through each of them like later, and just short description of it. So it turned out to be more secure because it's more auditable. I mean, would you rather prefer to read? Okay, well, we'll get to do it. It gets more auditable because it's like high level definition. It gets more upgradable because I mean EVM changes. You just get the production used EVM, recompile a circuit, voila, you did it. And like compatible. How much more compatible a circuit, like bytecode compatible circuit, can be if you compile that, like from the actual EVM interpreter. Of course, there will be like drawbacks, something you would be required to cut out. You would be required to inline something, but in general, it would be still the same code. And proof system will get into that. Performance will get into that because as they say, everybody gangsta until you show the proven performance. Then I mean, and what it powers and what we used it for, we'll get into that as well. So, secure, what does that mean? What I'm talking about, what I'm saying, production used EVM. I mean, EVM1 is basically one of the oldest EVM implementations available out there. And we were like, okay, it was used in Silkworm, it was used in Ethereum CDP implementation. It is still used in some execution layer implementations. So we kind of took it, patched it a little bit, but in general, still the same code, and compiled it to circuits. Okay, so that's like a nuance. That's what you should take. Okay, just don't replicate the logic manually. Auditability. Shit. Okay, there is like not enough of resolution here, but in general, okay, this is like basically it is supposed to be just a typical implementation of keycheck. Okay, like takes 20 lines or something. Of course, there are inlines. Of course, there are like internal calls or something. But in the end of the day, it's high-level code. And this is, I mean, guys, it's yours. It's yours, right? Keycheck implementation, like 500 lines at the beginning of keycheck, and there are like several thousand lines of keycheck in that. And would you rather audit this or like this one? So, I mean, both of them work, but like, what if? Okay? So, same thing, upgradability. Would you rather write this thing and upgrade this thing manually, or you would just compile this thing? I mean, please compile this thing. Bytecode compatibility, I have no better picture, but it's the same. Okay, so it's like how much more compatible it can get if you compile the actual interpreter, if you compile the circuits the actual interpreter. So you don't need to spend like years on achieving the full compatibility, which I don't know. As far as I know it's like you have it like already, but like with some nuances, as far as I understand, right, guys? Yeah. So that's the thing, and that's cool. The proof system. It's like, what proof system did we use? Whatever. What proof system did we use? I'll just describe it. We used the Plonkish arithmetization proof system, of course. Of course, it's like we've put some kind of AVC in there. It's like this is still like in progress and yada. But anyway, the proof system of ours, like we call it placeholder, it allows to switch commitment schemes behind it, like hash-based commitment scheme, or like hash-based commitment scheme, or pairing-based commitment scheme. So that's what it is. Circuits performance. What about the performance? Performance is, let's be honest, automatic circuit generation is still not that efficient as it is manually, as it is, with manual thing. But in general, the difference we observe is like, 10-15% in amount of constraints. So we hope to get it down once we get in like class or like approach with, proving the lookup table instead of proving the actual thing. So might be like, even better with automatic generation. So what do we use it for? It's like we use it for, the thing we rolled out. I don't know, rolled out. We started talking about recently is something we call zk sharding. It's basically like, we think we've figured out the way of how to um, do like, zk rollup alike second execution layer to Ethereum. Okay. So what is that? So, okay, I mean, yeah, it is what it is. It's a rollup which tries to scale Ethereum by being the second execution layer. And yes, we do provide transparent access to Ethereum data. So that's we securely. So that's like, get back into zkEVM, okay? So what does it mean? It's exactly what it is. It's like, since it's a sharded thing, since it's a sharded zk rollup, zk, like, execution layer, each shard is being proven to a primary one. It's like the order to it's like for proof generation is being in place like on a proof market. So like basically the market dynamics for the proof generation takes the cost, to currently possible minimum because it's market dynamics. And that's what it is. Let's go back. So scale theory of zk sharding, okay? What does it mean? It means that, traditional sharding stuff, that's what it is. It's like protocol level sharding, okay? Not application level sharding. Currently existing rollups are basically application level sharding, which still maintain fragmented liquidity. It's like we were like, okay, we'll just do protocol level sharding. There are nuances, but that's what it is. Modeled some performance. Yeah, let's get that. Yeah, that's market-based dynamics of proof generation for the sake of, just everybody's going to ask, how much proving that would it take? What is the finality for that? And, we just allow the market to reduce that themselves, Yeah, what does it mean? Like, what for we did it? We did it for the sake of trying to put onto layer 2's data intensive and high load use cases, not just, Ethereum applications or something, because this is like already there. So we did it for the sake of putting data intensive use cases as, sequencers, and like MEV strategies, intent solvers, block future auctions, and things like this. Let's go forward. Data availability. Of course, you're not a rollup if you don't have Ethereum data availability. So we have it basically for the primary shard, which is enough to restore the whole cluster. And it's like in case an application wants to have, like data availability for all its data, just all of it, including all the metadata and everything, an application can pay for it and like, just store it on ETH and like a usual thing. It's gonna be expensive. It's like upcoming PFP will make it better. But anyway, next thing, transparent access to Ethereum data. So yeah, how is that like, relevant? What we did with it? What does that mean? So that means that we basically try to maintain composability with Ethereum from each shard of ours. So that means if you want, like, for example, call some application deployed on the primary Ethereum from a shard of ours and get some response out and get some response from it and use it like on O2 or something, you can still do it. You can do it for read access and for write access. Like for write access, not in the first version, but we'll get to that. That's what it is. It's like everything we discussed. It's like literally step by step. And we are publishing like papers about this. We're publishing articles about this. We're publishing blog posts about this in the blog on the research section of ours. And feel free to come by. Ask. We'll show you. Everything's like out there. Everything's open source. Everything's and it's just traditional slides with we're publishing also here on Twitter. So feel free. That's what it is.
Thank you very much, Misha. That was a really nice talk. I think we have time for one quick question, if anyone wants to jump in.
Thanks for the talk. Can you explain the difference between zk sharding and L3, L4 approach? What you're doing differently?
Composability. It's like that's Composability is basically what differentiates them. It's like protocol level composability is hardly. I mean, it's hardly possible on like L3's whatever, like horizontal scaling, because you gotta put that through sequencer, and you will not be able to order that within the EVM application. So that means you still fragment the liquidity. It's like, and this is still like, walled garden. This still being a walled garden. We try to not to, create more walled gardens, but to, keep each shard composable with each other, so the liquidity stays, there. That's the thing.
All right. Sadly, we don't have time for any more questions. Thank you very much again, Misha, for the talk. Please.